The first application in which we're going to use significance testing is for means of large samples. And I want to walk through the exact framework that we just talked about with regard to large samples, and then we're going to talk about the different assumptions and ways that we have to work around smaller samples. So when I'm talking about a large sample, I'm typically talking of a sample that includes more than 30 observations. We need to make an assumption that this is quantitative data. Uh, for our purposes right now, I want to talk about doing a hypothesis test for a mean, though we can talk later on about how to do it with a proportion. The second step is to state our hypotheses, the first of which is going to be the null, that the mean that we find in our sample mu is equal to the mean that we believe to be the true underlying mean in the population. That's going to be represented by mu naught. This is technically a two-sided test, but you can think of ways in which this may be a one-sided test. Maybe we're just interested in whether or not the sample mean is less than the true underlying mean in the population. Then we'd have to set up our null hypothesis such that mu is greater than or equal to mu naught as our null. But again, this is just a different way of thinking about it. Right now, I want to concentrate on doing a two-sided test. Since we are doing a two-sided hypothesis test, we are going to subtract mu naught, which again is what we believe under the null hypothesis to be equal to the sample mean, which in this case is represented by y bar. And the difference between those two is over the standard deviation that we find in the sample. The TS is just an abbreviation for our test statistic. The test statistic that we use is going to change throughout the semester based on what type of hypothesis test we're using. So this is just one example where we're interested in looking at whether or not the mean of the sample differs from what we believe the true underlying mean to be. But the important thing to remember is that this test statistic is generated from the sampling distribution of y bar, or whatever the point estimate that we're comparing. With our test statistic in hand, now we can actually generate some level of surprise, right? And that's going to be our p-value. Essentially, all we're doing here is saying, is the probability that we get a test statistic, or what's the probability that we get a test statistic this large, and what's the probability that we would get a test statistic this small? What we're doing here is a two-sided test, so that's why we're doing above and below. We may be doing a directional hypothesis test, and we'd only look at maybe the top or the lower tail. Now, when I'm talking about the upper or lower tail, I again can't stress this enough. We are referencing the test statistic, which is generated from the sampling distribution, in this case of y bar. The center of that distribution, which is an assumption, right, is at mu naught, and the spread of that distribution around mu naught is going to be characterized by the standard deviation of y bar. So when we're talking about the upper and lower parts of the tails, what we're talking about is the center of the distribution, a given test statistic that we get. Is that sufficiently extreme enough that we would reject the idea that the true underlying parameter is mu naught? Remember, The p-value is referencing the sampling distribution of whatever the point estimate of interest is in our hypothesis test. Finally, if we do get a p-value that's low enough below our critical threshold, aka having a test statistic that is extreme enough for us to think that it is not actually mu naught, then we can conclude that the evidence supports the alternate hypothesis. What I would really prefer is that you would say that we have sufficient evidence to reject the null hypothesis. Now, if it is the case that our p-value is larger than our critical coefficient, then we should alternatively say we do not have sufficient evidence to reject the null hypothesis.